Hello, students. Welcome to chemistry. Some good news. We're going to do a lab today. So let's just quickly do the opening. Let's do the 5-minute lesson, and then we'll begin the lab. Opening. A tree needs water to live. A tree can be very tall. How does water get to the leaves on the top of a very tall tree? You might know the answer already. Please write down the answer to the best of your ability now. If you do not know the answer, I want you to guess. Please write your best hypothesis with complete sentences. Please pause the video now to do that. Okay, we are back. A tree needs water to live. Every part of the tree must be receiving constant water. And a lot of people believe the very top of the tree is getting water from the rain hitting it. The rain, of course, hits the very top of the leaves, and people think that these leaves soak up the water like a sponge, and that's how the water gets on top. But that would be wrong. That is not the way the top leaves get their water. The top leaves, all the leaves, get their water from this. Roots. So the water falls into the soil. It infiltrates the soil. It percolates in the soil. And then the roots, which reach down in the soil most of the time. In this picture, the soil must have eroded away, but I would imagine at one time these roots were underground, and these roots absorb the water, and then the water is transported through every branch and to the very top of the tree. If the transportation of water is not successful, the leaves will die. So when you see a tree with leaves at the very, very top and they're green and they're healthy, you know that somehow nature was able to get the water from the ground into the roots and then all the way to the top of the tree. How does the tree do it? Well, the answer is capillary action. Have you ever heard of capillary action? You might have learned it in a life science class. You might have learned it in a biology class, but let's go over it. Capillary action, or capillarity, describes the ability of a liquid to flow against gravity. Yes, to flow in the opposite direction of gravity in a narrow space, such as a thin tube, or the stem or branches of a plant or of a tree. That is capillary action. And capillary action is essential to life on Earth. It's very, very important that water can be transported around. And water can be transported around because of the very unique qualities of the water molecule. So let's go over the water molecule. Let's remember that the bonding of hydrogen and oxygen are two nonmetals bonding together. So it's a covalent molecule. And in a covalent molecule, we share electrons. So the electron of the hydrogen atoms is represented as an X, and the electrons of the oxygen atom are represented by these spheres. And oxygen has 1, 2, 3, 4, 5, 6 electrons, and hydrogen has 1 electron, 1 valence electron here, 1 valence electron here. Hydrogen needs 2 to be like helium, to be like a noble gas. So it needs 1 more electron, and it gets it by sharing one of oxygen's electrons. Oxygen has an oxidation number of -2 or 2 negative. So it needs to gain 2 electrons, and it gains 1 from hydrogen here, and it gains 1 from hydrogen here. And when it does that, it has 1, 2, 3, 4, 5, 6, 7, 8. That's what it wants. It wants 8 electrons in its outermost shell. So this is a very stable molecule. Some water molecules on Earth are billions of years old. And what's interesting is that when hydrogen has its electron bonded to oxygen, it makes kind of an exposure of the proton on this side. It makes this side a little bit positive and this side a little bit positive. And because oxygen has gained 2 electrons, it's going to be a little bit negative. So a water molecule, we'd say that it's polarized. It has a positive end and it has a negative end. And that's what gives water its unique properties for capillary action. So water is attracted to itself. A water molecule has a negative side and a positive side, and opposites attract. So the oxygen side of a water molecule tends to be attracted to the hydrogen side of another water molecule. They kind of line up like this. And that causes water to be attracted to itself, and that's what causes water to bead up. So this spider web isn't evenly wet. The water has kind of attracted each other and formed little spheres, and that's what causes water to bead up. Water is attracted to itself with this polarized quality, the idea that there's a positive end and a negative end. So here's another example of water beading up. Nobody made these little circles. Nature makes them because water has this polar quality. And water is not just attracted to other water molecules, water is attracted to other substances as well. That's what causes the meniscus in a graduated cylinder. The water is a little bit attracted to the sides of the container, and that's what causes this curve. So water is a little bit sticky. We think of glue as being sticky. A lot of times we don't think of water being sticky, but think about it. When you wash your hands, it's hard to get that water off. You can do this and the water will stay on your hands. Your hands will be wet for a while. You need to get a towel. And the reason the towel will get your hands dry is the water sticks better to the towel than it sticks to your skin. So now the water's on the towel, and try to get the towel completely dry. That is a hard thing to do. You're going to need the help of evaporation. So why does water stick to my skin? Why does water stick to a towel? It's because of the polar quality of the water molecule. So today we're going to do a capillary action lab. And I went over this last week, but let's go over it one more time. Materials needed. You will need a glass of water or a cup of water. Coffee filter paper. If you don't have any coffee filter paper, paper towel will work, a napkin will work, any absorbent paper. You need 1 or more markers. Sometimes a marker doesn't work for this, so it's nice to have more than one. You need a clock, a timer. You can use your cell phone or any way to time minutes. Use your computer, but have a way to be able to monitor how many minutes go by. And then you need a place to write or type your observations. Don't start the lab and then look for a pen, look for some paper, because then the lab will be going on and you won't have, you'll miss something as you're looking for your paper and pen. So just be all ready for the lab. And I just want to give a special thanks to Wikimedia Commons that provided all of our images today. That is the lesson on capillary action. Let's begin the lab. Your coffee filter paper, and you will need to cut it into a rectangle. And that rectangle should be about maybe 1 or 2 inches wide and maybe about 4 or 5 inches long. And the dimensions can be a little bit different than what I just stated, but you want something that's going to look like this. If you don't have any coffee filter paper, here's a paper towel. You don't need all of this. Again, you want to cut just a rectangle, approximately 1.5 inches wide, and that is maybe, it looks like that's about 5 or 6 inches long. Okay, if you don't have any paper towels, here's a napkin from a fast food restaurant. I know I'm supposed to be social distancing, but I went to a place and got some coffee. Was that scandalous of me? And I never did the lab with paper like this, but it's absorbent. It should work. Okay, but the best thing is the coffee filter paper. That works really nicely. Now you need a marker. And I said a black expo marker, like a dry erase marker would be best. I actually don't have that here. All of that is in my classroom. So I was looking around hoping to find something, and I found this. It says Sharpie, but it's going to work. And then I found a blue Sharpie. It's best if you have black. I don't have black, and you know we're all working at home, doing the best that we can do. And I have brown and blue. That's actually going to be pretty good. And what I want you to do is to draw a line at about the 60% mark. Not in the middle so much, but a little bit above that. So I'm going to do that. And make it nice and thick and dark so that you have a stripe in magic marker that looks like this, and then you place it in water. You don't want to put it in so deep that the water gets the marker all wet. Instead, what you want to do is just put the tip in, and what's going to happen is capillary action is going to bring the water slowly up, and eventually it's going to pass through the ink from the magic marker, and something's going to happen. So that's what we want to observe. If you have more than one marker, some markers don't work for this, so it's nice if you can try different things. I'm going to do another marker right now. I'm going to do my blue marker, and I'm going to make a nice dark blue mark on my coffee filter paper, and I'm going to put that in the glass as well, just like this. Again, we want the water to come up. We don't want the whole coffee filter paper to get wet. We just want the very bottom, but according to the rule or the law of capillary action, the water will rise up naturally. It's going to take a while. It will take approximately 5 to 10 minutes, and it depends. Different papers respond differently. But eventually, you should see something. Do you see that? This is the coffee filter paper. I had put brown ink on the coffee filter paper, and as the water is slowly coming up, it's spreading out all the different chemicals that make up the marker ink. And you can see that the marker ink is not just brown ink. It looks like there's a lot of pink and orange, and on the bottom there is that a little bit of blue-green. So to make a brown marker, you actually combine several different colors, and these different colors migrate at a different rate, at a different speed. And one of the questions in the lab is, why is that? Why does that happen? Okay, and here is the filter paper with blue, and it looks like that there aren't different colors in the blue ink, and that's interesting to learn too. So this is a way of analyzing how different chemicals are formulated. All right, I want you to write in your lab why you think this phenomenon happens. Why is it that certain colors migrate a far distance and other chemicals, other colors do not? Go to one of my favorite periodic tables of elements that's online. It's called P-table, or the dynamic periodic table. I hope you remember this one. And the question is, why do some elements migrate faster or slower during capillary action? And I want you to come up with a good hypothesis. So let's think about the different properties for elements. Let's click the Properties tab here, and here's a whole bunch of properties of elements. So maybe it's electronegativity that's causing the different speeds. So do you remember what electronegativity is? If you don't, there's no problem with that. You just look it up. Electronegativity. Oh, there it is. And there's a Wikipedia page on it. Here's a definition. Here's a different source. So you can find out what electronegativity is, look up the definition, learn a little bit about it, and decide if maybe that's the property that's causing this interesting phenomena today. Let's look at other properties. Here's density. So different elements have different densities. Maybe it's the density of the chemical that's causing it to migrate at different speeds. So go through these different properties, maybe go to another source and find even more properties of elements and compounds, and then come up with a hypothesis why you think the different chemicals migrate at different speeds because of capillary action. I hope you enjoy the lab. Do a real good write-up so that I can give you a really good grade. Good luck.